Public lecture is an important part of what a scientific community does to explain to the public, to senior officials, even the highest officials, what it is we're doing, its importance, why it's important, and the ability to communicate in plain language the challenges that we face as scientists and engineers really requires a special skill. And so we have many distinguished visitors here, and when we choose a public lecture, we choose somebody who we know has a track record not only of first-class science, but also ability to explain that in a very accessible fashion. Although I must say that this year, the plenary lectures and even the contributor lectures have, the people who have made those lectures have done a terrific job in framing the work that they do for the general audience. I do want to say that Canada actually has done surprisingly well. Some of you may have seen this viral video. I'm going to see if I can play it.
I was going to ask you to explain quantum computing, but when do you expect Canada's ISO mission to begin again? And are we not doing anything in the interim while we prepare?
Okay. Very simply, normal computers work by... Don't interrupt me. When you walk out of here, you will know more. Well, no, some of you will know far less about quantum computing, but most of you, normal computers work either there's power going through a wire or not. It's 1 or a 0. They're binary systems. What quantum states allow for is much more complex information to be encoded into a single bit. Regular computer bit is either a 1 or a 0, on or off. A quantum state can be much more complex than that because, as we know, things can be both particle and wave at the same times, and the uncertainty around quantum states allows us to encode more information into a much smaller computer. So that's what's exciting about quantum computing. And that's
So actually, he was at the Institute for Quantum Computation announcing a awarding of 50 million Canadian dollars, approximately the same as US dollars, maybe a little bit less. But very important funding, but also understanding at the highest levels of the importance of quantum computation. So I've asked our Dean Cooper from Dietrich School of Arts and Sciences, who has been, from the very beginning, consistent supporter of the Pittsburgh Quantum Institute, to deliver some introductory remarks and to introduce the person who will introduce our public lecture.
Thank you very much indeed, Jeremy. I'm always delighted to be here at PQI and to see what a wonderful event this has been, is now, and will continue to be into the future. I do keep asking Jeremy to actually get down to grips and quantify for me what the expectation value of PQI might be. And for some reason, he seems to find this a very difficult sort of task. And the default, being a dean, is that, of course, that means I must have extremely high expectations of PQI, because what else could be true? And maybe that's what keeps me coming back every year to do at least a brief introduction to all of this. But since Jeremy was being a little elusive on some of these expectation values, I thought that I would really need to bring my own to this particular event. So I do have, it's a public lecture, so presumably the speaker would not mind if I asked a few questions or set up some expectations as to things I might learn from all of this. So we have some questions that with a little help, have been composed. Clearly, of course, the burning question, the discipline is, when are we going to have a truly scalable quantum computer? That's, I think, the core and most general of these questions. But then, of course, there are these immediate questions. I really would like to know your immediate plans to increase the frequency of transmode qubits and to improve the dispersive shift uniformity, which I understand is going to be a key technical parameter. And there are then broader implications that sort of come out of stuff like this, like how does the prospect of quantum computation impact the P equals NP conjecture, and how will that in turn shape our understanding of complexity theory? Or we could go towards the gravitational question and say, to what extent does quantum gravity impose an informational friction on the universe, tying into our astronomical colleagues? And what limits does this informational friction place on large-scale entanglement? Either I was prompted with complete garbage, which is perfectly possible right here, or you don't actually believe I wrote those questions, which would be true. However, PQI is a wonderful event. It's pulling together students, faculty, and graduate students from all across Pittsburgh and from all across the world. We're very privileged indeed to have Michel join us today. And having demonstrated my lack of ability to ask intelligent questions, I'm going to, I hope, intelligently delegate to Michael Hatridge, who worked with Michel for 5 years, the task of providing a more formal introduction.
So at the risk of a repetition, I'm going to try one more joke. Michel actually answers all these questions very regularly. The only trick with Michel is often that they are the answer to the question, what are we going to have for lunch? Okay. I've known Michel for a dozen years. He is a kind and generous man. He will even forgive me for this introduction. He is from France, as you will soon discover. He did his PhD with Abraham, working on solid-state NMR. He then moved to California, doing a postdoc with John Clark, where I got my own PhD, working on these groundbreaking experiments in macroscopic quantum tunneling that set then the foundation for his follow-up work, where he formed the Quantronics group at Saclay, working to really explore the beautiful mesoscopic physics that's possible in these superconducting Josephson junction systems. He, while he was there, did some of the pioneering charge qubit work on the so-called quantronium qubit. In 2002, he moved to Yale, worked together with Rob Scholkoff. He has formed really a powerhouse, both mesoscopic physics and superconducting quantum information group. He has numerous prizes, numerous academic memberships and esteemed societies. I just want to highlight 2 recent prizes. One, he won jointly in 2013, the Bell Prize with Rob Scholkoff, and in 2014, the Fritz London Memorial Prize with, again, Rob Scholkoff and John Martinez. And he's here today to tell us about the quest for the robust quantum bit.
Okay. So, good afternoon, everybody. I would like first to thank the introducers, the three-tier introducers to my lecture, and also thank the organizers of this conference for giving me the opportunity first to participate to this very interesting meeting and tell you about some exciting new results that we have obtained at Yale University. So we need to switch this, okay? No? Okay. So, as you can see, I have entitled this talk, The Quest for the Robust Qubit. And what I hope to convey this afternoon is the sense that there is a new phenomenon in quantum mechanics, or I would say collective quantum mechanics, that is both extremely new and still, for the most part, not observed experimentally, even though the theoretical prediction is about 20 years old. And what is this new effect, new phenomenon? It's the fact that it would be possible, in principle, to have an effective two-level system that would live forever. This is what I call the robust qubit. In nature, every quantum system undergoes decoherence. There are no systems in nature that have an infinite lifetime, a coherent lifetime. Yet, it has been proven by Peter Shor in the middle of the 90s that, in fact, it would be possible, given enough resources, this is an existence proof, actually, to have a qubit that lives as long as you want. And of course, the longer the lifetime, maybe the more resource that you have to assemble. But the resources would scale modestly with the length of the lifetime. In fact, it would scale logarithmically with your desire to increase the lifetime of the qubit. So this is at Yale and in other places, we have embarked on the task of observing this quantum new phenomenon. And one idea that I want to communicate this afternoon is the fact that, surprisingly, in this quest for the robust qubit, dissipation plays a crucial role, in fact, a central role. And that's somehow paradoxical because we are used to think that dissipation is actually an important part of this coherence mechanism. So I would like to introduce the people whose work have been crucial for the results that I am going to present this afternoon. So there are two experimental teams, the team of Rob Sholkov and myself. And then we are benefiting from the help of several theory colleagues, Steve Gervin, Yang Zhang, and what I will be presenting today is actually owes a lot to Maziar Mirami, who works part-time in Paris and part-time at Yale. And last, but not least, I would like to mention the work of Michael Hartridge, which has been instrumental in this endeavor. And Michael has moved a year ago, we will say, to Pittsburgh. I want also to mention, for completeness, that we have this industrial partnership with a startup, Quantum Circuits Incorporated, which some of us have co-founded. Now, my talk will be divided in three more or less equal parts. I want to introduce some more this new collective quantum effect, which is sometimes known as quantum error correction. Then I will present our own version, our own thoughts on the way quantum error correction is done. It's quite different from methods that other people are using in both superconducting circuits, but also atomic physics. And then I will show you our latest result, which show that we've gone a long way into realizing the observation of this effect. Okay, so let's start as simply as possible. And you all know that the element of quantum information is the qubit. In fact, this is what was discussed by Pierre Trudeau. So I'm going to paraphrase what he has presented for a while. So indeed, a qubit is a superposition of a quantum superposition with two states, and a qubit is actually a quite complex object because the quantum superposition are parameterized by two angles. So basically, a qubit is analogous to an effective spin 1/2 particle. It is, you can look at it as a vector of unit length or a point on a sphere. And so this is a rich encoding space. And you can view the various operations on the qubit, the various properties of the qubit as basically the magnetization of that spin along three orthogonal axes. And this location of the quantum information is often referred to as the Bloch sphere. Now, the Bloch sphere is a two-dimensional manifold. It's a little bit subtle, so I'm going to resort to this simplification. Instead of the whole skin of the sphere, I'm going to take its skeleton, the skeleton of the sphere. You can think of it as this octahedron, and all the vertices of this octahedron are states which are eigenstates of the X, Z, and Y operators, the independent component of the magnetization of this effective spin. So this is what we call the cardinal point on the Bloch sphere. Now, in this language, decoherence can be seen as a perturbation of this octahedron. So if you start with your pristine quantum information here, there are different processes that are going to destroy this information. And those of you who have studied NMR or EPR know that there are T1 processes where everything goes to the North Pole here. So the octahedron is deformed and shifted to, is reduced inside and shifted to the North Pole. But you have also what is called the dephasing processes, in which the octahedron is compressed around its equator here. And it will then become just reduced to a line. So these are two decoherence processes. There are three independent noises along X, Y, Z that actually describe all the possible things that can happen. And the discovery of Peter Shor can be summarized by one sentence. Basically, it would be possible, in principle, to find a large Hilbert space in which you can encode this two-level system. And with the proper encoding, you should have an arbitrary long time for the coherence of the system. And there were many subsequent work which basically amounted to the fact that a quantum computer could be built. This is absolutely important because for quantum computation, because if you cannot extend the lifetime of all the qubits for the length of computation, well, the quantum computer cannot work. So this discovery is absolutely central to quantum information today. So we can I'm going to give you a sort of geometric image of what Peter Shor demonstrated. Basically, the qubit lives in a Hilbert space, and I have seen, as I have shown you, the loss of quantum information is the distortion of this octahedron. But if you choose the proper encoding, then you can arrange so that all elementary errors will not deform or shrink the octahedron. They will just translate it in Hilbert space or rotate it so that the information will be conserved. That's the essence of the proof. Of course, you cannot let this drift here happen forever. If you let this motion happen, there will be at some point some collision with the boundaries if you want, and then you will get distortion. So what it is essential in quantum error correction to detect these elementary errors, which at first order are not destroying information, and then to stabilize the system back into place. So this is an important conceptual step. You can think of quantum error correction as a sort of feedback problem. It's a stabilization problem. You want to stabilize not a state. That has already been done. Laser cooling is stabilizing a state, generally the ground state of a system. Here you are stabilizing a manifold. It's a whole manifold of states that you want to stabilize in this abstract Hilbert space. But basically the way you think about feedback in general can be transposed to quantum error correction. So for many years, the question has been, well, what systems will support, will allow you to implement this encoding? And today, I think it's fair to say that there are two main contenders. Superconducting quantum circuits, which I'm going to briefly describe here, and trapped ions. So those are the two main contenders en route to showing a proof of quantum error correction, a full proof of quantum error correction experimentally within just a few years. So quantum superconducting circuits are basically essentially ordinary circuits which are superconducting and which can behave as artificial atoms. They are based on various circuits elements which you know, capacitors, inductors, but you have to include a Josephson junction that's symbolized by a cross here. It's a nonlinear inductance. And this system behaves as an atom and can be read by microwave techniques. So there is, to this system, we first have a control pulse here in green that will shift the system from state to state. And we read out the state of the atom by sending another probe pulse, whose frequency doesn't coincide with the atomic transition. And these pulses are shifted in phase. And the key element in the readout of these atoms are amplifiers that function with the minimum noise allowed by quantum mechanics. These are these Josephson preamp, and Michael has been instrumental in developing this technique. The way you can look at this readout is that the atom here in green will confer to the whole circuit a resonant frequency which shifts with the state of the atom. So if you study the resonance, if you measure the resonance of microwaves going through the circuit, the maximum of the resonant frequency will shift with the atom level, G or ER, the atomic state. You can look at this phenomenon also in the phase, and you have a more or less a pi over 2 phase shift when you transition from the ground to the excited state. What is remarkable with this superconducting circuit is not their absolute level of coherence. They live a fraction of a millisecond at present, whereas their competitors, trapped ion, live at least 1,000 times larger. But where the two systems are really very close is the ability of the control ability. So you see here is a quantum jump experiment where a qubit, here a transmon qubit, is monitored in real time. And what is important to notice here, so for instance, the black trace is a particular history, jump history of the qubit. The gray trace is another one. And you see the jumps from the ground to excited states are very well resolved. What is important to note that in these experiments, the readout is extremely efficient. 90% of the fluctuations you see here are intrinsic quantum fluctuations of the signals that are sent to the atom for its measurement. So what you see, the fluctuations you see are exactly analogous to the shot noise of a photomultiplier in a quantum optics experiment. Fluctuations that are not due to the imperfection of your readout chain, but which are intrinsic quantum mechanical effects. And the readout, as you see, is very fast compared with the qubit lifetime. The qubit lifetime you see is of order 100 microseconds, but we can monitor it on a rate of a fraction now of 100 nanoseconds. So in fact, you can acquire 2,000 bits of information on the environment of the qubit during its lifetime. So you have a close real-time monitoring of a quantum system. And this is absolutely essential for quantum error correction. Now, I have to say that the bulk of the experiments that aim at prolonging the lifetime of a qubit are done with the so-called method of the register of qubits. So what happens in these experiments that are performed at various labs here basically copy what happens with classical error correction. So you encode your quantum information not in a single qubit, but in a register of qubit. The minimum is more or less 7. And you submit this register to various measurements that detect syndromes, and depending on these error syndromes, you apply correction. We follow a completely different strategy, which we think is not as greedy for resources. It's what we call these methods hardware efficient. Instead of using the Hilbert space of a register, which grows exponentially with the number of qubits, we use a cavity resonator. We use an harmonic oscillator, basically an electromagnetic superconducting cavity. And we encode quantum information in this system, which, as you know, has a certain number of has an infinite number of levels, each level corresponding to a certain number of photons in the resonator. And we have we've called this idea, this particular implementation, we've called this the CAD codes. And you'll see in a minute the relationship with Schrodinger cat. Just to motivate a little bit why we wouldn't do like everybody else, let me show you in the example the register of 7 qubits, which is called the Steen code, how this particular quantum error correction encoding works. So in this diagram, every hexagon here represents a qubit. So you see there are 7 qubits, and I have arranged them in a sort of projection of a cube. There are 3 faces. Each face has 4 qubits. And the 0 and the 1 logic are extremely clever entangled states of this 7-qubit register. To get an idea of the subtlety of this encoding, I will ask you to look at each of these faces in all the terms of the superposition. And if you count the number of 0 and 1, you'll see that it's always an even number. So there are a certain number of symmetries here that are implemented, and it is these particular symmetries which allow individual hardware errors to just give you this translation of the quantum information that is repairable. Actually, the repair is not that simple. So we have each qubit is now a lifeline here, an horizontal lifeline. And you need 6 ancilla qubits in order to detect 21 error syndromes. And this you detect by these four-way parity operations, which detect on the plaquettes whether the product of Z operators or X operators have changed. There are 21 channels for errors because each qubit can have errors along X, Y, and Z. And there are 7 qubits, so that's 21. And 21 type of errors can be encoded on 6 bits. And in real time, you have to measure those 6 bits of parity and decode them and find the errors and correct it. So you see, it's a rather complex feedback loop. So I'm going now to switch to this cat code encoding and tell you how we can use a cavity, only one cavity, to encode in an error-correctable way quantum information. So what I'm representing by these patterns is the phase space of an oscillator. So you know an oscillator can be characterized by X and P. I can think also here of I and Q as the electromagnetical analog of X and P. It can be the charge across the junction or the current through the junction, or you can also think about it as the in-phase and quadrature component of the oscillation of the cavity. Now, classically, the ground state would be a point in the center of this phase space. Quantum mechanically, because of quantum noise, you have a disk here, not a point. So that's the ground state of the cavity. There is an excited state, which we're not going to use, which we could use to implement the one state. And that's the state of the cavity with one photon. And this is representing here using the quasi-probability distribution of the cavity, which is also called the Wigner function. You can think of it as the probability to find the system in this phase space. But of course, it's a little bit more subtle. This is a quasi-probability. It can be both positive, which is the red here, or negative, which is the blue. And the reason why you need the blue, well, you need to make a state that's orthogonal to this one. So if you would multiply the two figures and integrate, it would be 0. Now there are other excited states of the cavity. Instead of the vacuum, you can create what is called a coherent state, which is just a displacement in phase space of the vacuum. That's an excitation, which doesn't correspond to a well-defined photon number, although we can characterize it by the average, the mean displacement here from the origin. This is what the 2 means here. So that's a coherent state, also called a classical state, semi-classical state. We also have the squeezed vacuum, which is the ground state, but where the quantum fluctuations have been squeezed in one direction and anti-squeezed in the orthogonal direction. But of very interest today is what is called the cat state. So a cat state is a coherent superposition of 2 coherent states with opposite phase. So it's the way to imagine it is that an electromagnetic resonator is analog to a pendulum. So a coherent state is just a coherent oscillation of the pendulum. And the cat state would be actually the pendulum in a superposition of 2 states with opposite phases. So as you see, the pendulum, if it would do this, when the 2 versions of the blob, the 2 superposed versions of the blob would coincide at the bottom, there would be an interference pattern. And this interference pattern corresponds to the fringes you see here in the Wigner function. And we call this a cat state. In all truth, it should be called the kitten state. but we call it a cat state nevertheless. What is the link between this kind of state and Schrodinger cat states? Well, you see, if you had a pendulum, and the oscillation of the pendulum would contain something like an Avogadro number of excitation of photons, well, you would really have a superposition of the pendulum in two completely different macroscopic states, exactly like the Schrodinger cat. In fact, at Yale, we've made cat states where the number of excitation involved is 100, which is not the Avogadro number, but it is this kind of macroscopic superposition that are behind the Schrodinger cat. Here, in our cat code experiment, the number of excitation will be more like 5 or 4 on average. Okay, so that explains now the reason why we are calling this the cat codes, because we're going to encode the 0 logical and the 1 logical as two different cat states, which are dephased by pi over 2. You see, if you look at this cat and this cat, they correspond to two oscillations of the resonator shifted by pi over 2. So let's see what happens when you wait for a time which corresponds to a typical error, which corresponds to the rate at which errors happen in this system. This system is very advantageous in the fact that there is essentially only one error channel. The only thing that can happen to the cavity, mostly, is actually that it can lose a photon. So my representation here typically pertains to a time which corresponds to a lifetime of the resonator. And after one lifetime of the resonator, the probable evolution is the following. So your cat has shrunk, your oscillation has decreased, so that corresponds to simply a decrease of the energy of the system. And there is another thing that happens. Because the system has lost a photon, then there's a phase factor that has crept in. You see, because you superpose two states with opposite phase, there's a minus sign that appears here, and the minus sign actually corresponds to the fact that you go from an even to an odd cat. What does this mean? Well, this even cat, which corresponds to a fringe being red here in the middle, has an even number of photons. The number of photons is undetermined, but something is determined, which is the parity of the number of photons. And when you have lost a photon, that number has gone from even to odd. And an odd cat is characterized by a blue fringe here in the middle. So this is something that has happened to the state. Because of this I factor here, there is a pi over 2 phase shift that has come up in any superposition between these two states. So what has happened is two things. You have decreased the energy of the system, and you have had this pi over 2 phase change in the superposition. So this is something that you have to watch. You cannot really keep these changes go on forever. But what is remarkable is that to first order, you have not lost any information. So this process here is really the translation of the octahedron pretty much a little bit further in phase space. So it's still correctable here. So this is what we are going to use. And if we go back to the Bloch sphere and the octahedron of the Bloch sphere, let me show you in phase space what are the 6 cardinal points. So the plus z and minus c eigenstates correspond to these two-leg cats shifted by pi over 2. But the states on the equators are quite remarkable. They correspond to these more complex interference figures, which we also call four-legged cats, because they have 4 blobs. And these four-legged cats have been observed in a certain number of experiments already. So now I'm going to tell you that how we repair these errors. So now that we have this encoding, how can we monitor the errors and repair them? So as I've said, I've told you, there are 2 things we have to watch. So the cat is shrinking, it is losing energy, and so we have to repump the cat. We have to make sure that the oscillation stays with the same amplitude. That's very important, because we cannot let the number of photons decay forever. At some point, when there's no oscillation, 0 and 1 state become non-orthogonal. So we cannot let this shrinking go to forever. And then we have to do something about this parity jumping that corresponds to a phase shift. In practice, the type of experiments we do are shown here. So there is a superconducting resonator, which is this cavity here, and which is going to hold the information. So this is basically where the encoding takes place. And adjacent to this cavity, there is another cavity, which, as you can see, is bigger. This is what we call a reservoir dump, a radiative dump. It's a cavity with a big hole here. And the reason why this cavity has to have dissipation, well, you see, all these errors correspond to entropy, and entropy has to be evacuated. So we need some dissipative channels here to remove the entropy. And this hole actually communicates with a waveguide, which is a Purcell filter, which I won't describe. But what's important is that at the end of this waveguide, there is actually a connection to one of our amplifiers, whose chip is represented here. And this amplifier is what allows us to monitor in real time the information lost by the system. In this type of experiment, the qubit which correspond to this Josephson junction, whose micrograph is seen here, is not the location of the quantum information. So this is very important. We don't encode the quantum information in the Josephson junction. The Josephson junction is here only as an ancilla, providing enough nonlinearity to do operations on the locus of information, which is a superconducting cavity. So this is quite a different type of idea. So the transmon is not actually where the information is stored. The transmon is used to correct the cavity. And this is the schematic of the experiment. The storage is where the information will be located. It is actually encoded in a T10101 mode. And the radiative dump is another cavity of slightly larger, which corresponds to a lower frequency. And the qubit, the transmon qubit here, provides a coupling between the two. The coupling is an interesting form of coupling, and we are going to use this type of coupling. This coupling is able to take 2 photons in the storage and together transfer them in the radiative dump. And we're going to use this elementary process. So to tell you how we use it, I have to go back to the elementary physics of the driven damped oscillator. So this is a very elementary mechanical problem. We have a pendulum here. It hangs by a string. I'm going to move the string to give energy to the pendulum. And the pendulum is in a frictional medium. And it receives from this medium a frictional force proportional to velocity. So when I drive this system in this dissipative medium, I get a steady state, which I can represent in phase space. And the amazing thing about this system, and you have really to think about this because this is a crucial idea. Quantum mechanically, instead of this dot, you have a quantum state which in the limit of a high Q system is a pure state. Now comes really something that is surprising and that one should meditate. When you drive and dissipate a quantum harmonic oscillator and the Q is high, and here the Q is greater than 100,000, this system, even though it is in contact with friction with the reservoir, is actually in a pure state. Basically, the drive energy goes through the system, is dumped in the dissipative part, but the system is in a steady state that is pure. That's quite amazing when you think about it. It's elementary, but it's a very interesting property. How is this state determined? Well, it's very easy. It's exactly like in classical mechanics. This state results from the competition between the drive and the dissipation. So quantum mechanically, you have a drive term here, you have a loss operator, and the state that will be the steady state, the pure steady state of the system, has an amplitude which is just the ratio of the drive to the dissipation. Okay, now we can generalize this idea, you see. Now let's imagine a pendulum that is driven in a way that doesn't know about the sign of the phase, that essentially is able to communicate energy of the system in a way that doesn't know from right to left. So it creates a superposition of state. And at the same time, we've changed the dissipative medium in such a way that it is now a dissipation, a frictional force that's not proportional to velocity, but to the square of the velocity. So that's going to be dissipation, but a dissipation which is blind to whether the pendulum is on the left or on the right. And this kind of driven damped oscillator creates a cut. In fact, it creates a cut that can be either even or odd. It creates actually two cuts, or if you want, it creates two blobs here, which with no possibility of distinguishing between them. Now you have the ratio of this two-photon drive and this two-photon dissipation, but the amplitude of the blob is given by the square root of the ratio, and the square root have two solutions. So you are stabilizing here not one state, but a manifold. So you've created a system which admits a whole superposition of state as a steady state. This is a completely new situation. This is a system that is driven and dissipative, but which has two states, two steady states that can be superposed, and the driving and dissipative mechanism cannot distinguish between these two states. So this is exactly what we need to maintain the energy of our cat. And very briefly, it is realized by the Josephson junction in the following way. So I have told you that the Josephson junction is able to take two photons at a time and transfer it from one resonator to the other. So if we pump the system, we can substitute one of the photons by this drive and then transform our Hamiltonian into an effective Hamiltonian, which takes two photons from the storage and creates, transform these two photons in a photon that is going to be emitted in the radiative dome. So this is how we create two-photon dissipation. And by applying a drive to this radiative dump, we can create the reverse process and we can create a 2-photon drive. So basically, our initial Hamiltonian will give us what we are looking for, this drive and dissipation that is not proportional to the velocity, but to the square. And that corresponds to taking 2 photons at a time instead of 1. Now, have we really created these 2 dips in phase space? So we've created, in phase space modulation, we've created an artificial potential, a dissipative potential, that admits 2 locations. And this is borne out by these experiments where we have prepared, in absence of drive and damping, a given semi-classical state in the cavity, and then we've turned this 2-photon drive and dissipation. And as you can see, whatever the initial state, we end up only in these 2 locations here. So by doing this experiment, we can map the attractors in this phase space, and we discovered that there are 2 stable attractors and 1 stable and 1 saddle point. So the location of the ground state, of the vacuum state, has been now switched to a saddle point which is unstable. This instability of the ground state is actually observed in this experiment. So we start from the resonator in the ground state. These 3 panels correspond to the raw data. We can measure this Wigner distribution. We can filter the raw data and get what is called the reconstructed density matrix of the system, and basically a cleaned up Wigner distribution. And these are the results of numerical simulation. And as we go on here, I'm going to pump the system. And you see that at the beginning, I'm going to just squeeze the ground state. So I'm just elongate the ground state because the 2 minima are not far enough apart. But at an optimum time, I actually create the system in this superposition of 2 steady states. And in this experiment, you will notice that there is a little bit of negativity which signals the quantum interference between these 2 stable dissipative states. Of course, in this experiment, there is still the 1-photon dissipation. So we are actually, as we stabilize the cut, it is still losing information due to the 1-photon losses. So if we keep on pumping, this phase shift due to photon loss, they scramble the interference pattern, and in steady state, we will just have an incoherent superposition of the 2 blocks. But these results were obtained along 1 year ago, which is a fairly long time in our field. And since then, we've been able to actually improve the experiment much better. We now have a ratio of the 2-photon dissipation, which is the good dissipation. It is the dissipation which allows correction, to the 1-photon dissipation, which is the errors. And now it's about 100. We've also lengthened the time of the cavity. And now we can get fairly good agreement with theory. In particular, you will see that the middle fringe now is brighter than the 2 blobs, something that is quite essential. There's a little bit of distortion due to the Kerr effect, but this is a pretty good realization of a superposition of 2 steady state of a dissipative system. So if you want, you can have a system that continuously dissipates energy and yet is in a superposition of state. now, I have told you that we have these parity jumps. So we have, can we correct for those? Yes. So this is something that has been done in Rob's group. And it is based on the fact that we can measure in real time the parity of the photon number of the cavity. So let me just remind you that this parity operator counts the number of photon modulo 2. So it ignores the exact photon number and subbase of the storage cavity, but changes from +1 to -1 when you go from even to odd cat. And in fact, this parity operator is related to this Wigner distribution that are so useful to characterize what we do, because actually the Wigner distribution is just a shifted measurement of the parity operator. In this parity measurement, the qubit is going to play an essential role. The transition frequency of the qubit are shifted proportionally to the photon number, and we can distinguish the lines corresponding to the even number of photons in the cavity to the odd number. Now, by applying a pi/2 pulse that rotates all these transitions at the same time, which is indicated here, and waiting a time which corresponds to pi over this chi phase shift, we can condense the state of the qubit into orthogonal state depending on whether the cavity is odd or even, and as pioneered in the group of Serge Haroche and Jean-Michel Raymond. And with this kind of parity measurement, we can actually, in real time, detect the errors of the cat and correct them. This requires fast electronics based on this field programmable gate arrays. And these are the summary of the results. So in this experiment, we're going to compare different type of encoding. We're going to first encode the quantum information in the qubit that is the ancilla. So it's a transmon, and this is the octahedron, initial octahedron that is correspond to the encoding of 6 states. So I'm representing actually what is going to happen to these 6 cardinal states. And so this is the initial configuration. We can do a measurement after 6 microseconds, and the transmon doesn't have a very long lifetime, so the information actually shrinks very rapidly. After 110 microseconds, pretty much all the quantum information is lost. The fidelity of the memory process has gone down to essentially 25%, which corresponds to a total loss of information. Now, let's encode the same amount of information in the cavity in a cat state, but let's not apply any quantum error correction based on parity. And this information is also going to shrink, but because the cavity has a longer lifetime, after all, it's a superconducting resonator, and those systems have a very large Q. After the same time, now the fidelity is much higher. But if we now encode the information with the same cat, but actually correcting for these parity errors using this fast monitoring and feedback electronic, actually, as you will see, after exactly the same time, the fidelity has increased. So we've actually really corrected the errors in real time. So why don't we claim a total victory here? What we say here is that we've reached a break-even point. In fact, this amount of fidelity is what you would obtain if instead of encoding your quantum information in the cat, you would have encoded it into a superposition of 0 and 1 photon. The rule of the game, you see, is that you have to prove that your new qubit, your effective qubit, is better than any part of your system used in any encoding. This is really what would be the progress would be to beat every possible encoding based on one particular part of your system, because quantum error correction is a collective quantum effect. So the collective qubit has to be better than any of the parts that you use. So, but still, this result, to the best of our knowledge, has never been obtained in any other technologies, any other implementation. We have reached break-even point. So we are able to maintain the lifetime of a logical qubit for as long as the best part of the system, which is a very important step en route to full quantum error correction. So this is basically, these are my conclusions. I have shown you one solution to perform quantum error correction, which is not too hungry in terms of resources. The full implementation will require 1 or 2 cavities and 2 or 3 transbonds. We are still figuring out the optimum. I've shown you that we can do this autonomous stabilization of code space. We can, by this driven dissipative process, resupply energy in our logical qubit. We can monitor in real-time parity and correct it. We've reached this important stage of break-even for quantum error correction. Something that I didn't have time to cover is that it's not just a memory. This cat code can actually provide logical qubits on which you can perform gates. For instance, we have entangled 2 of such logical qubits. Of course, there are many things that remain to be done. We have to combine cat pumping and parity monitoring. And also, I think on the way to this holy grail of the robust qubit, we have to be able to do gates while we are correcting. This is called fault-tolerant quantum operations, and this will be, when successful, this will represent the last stage that will allow a fully scalable quantum computer to be built. And that would answer one of your questions.
Thank you.
Okay, thank you very much for your attention.
Questions for our speaker?
So, really beautiful stuff. And am I correct in understanding you that basically each logical qubit will require kind of 2 centimeter scale superconducting cavities?
Yes. So, this question of sizes is sometimes asked, and let me repeat the question. So, the question is that the systems that we are using seem to be based on superconducting cavity that are fairly bulky. Yes. So, but you have to take these cavities that indeed look centimeter inside as just first prototypes. It is possible to miniaturize these cavities remarkably. So a superconducting cavity, instead of machining in a bulk metal like this, can be made with 2 wafers that are bonded together. This is a more sophisticated technology, but it has been demonstrated. We're just trying to do at the moment the most simple experiment. So there was this first question.
Yes, you brought us sort of to the end that you hit the threshold,
Yes.
and then it wasn't quite clear what you need to do in the next steps. Can you sort of, give us a hint? Do you add more dissipative cavities around?
In fact, a message that I absolutely need to give here is that this field of superconducting qubits is absolutely not seeing any fundamental limitation. So every characteristic of the system, and today, can be improved tomorrow. We're just basically things continually improve. The lifetime of the qubits, the lifetime of the cavities. We have still a long way to go. Superconducting cavities can have Qs of 100 billion.
So that one of your ways is then to improve
we can basically in these experiments improve the quality of every element. It just requires more work. We have to assemble systems that to be made more carefully, but this is something that is happening on a yearly basis. I hope that I can, the fact that we have improved the figure of merit of the pumping by basically 2 orders of magnitude in 1 year tells you how fast the progress can be made. So we're very optimistic as to where these experiments are going. It's just a matter of work, pretty much.
But in addition to improving the Q of your main cavity, you need to sort of improve on the Josephson junction part of it.
That's an interesting question. So by far, the junction is not the worst part of the system. Actually, no one has ever seen any intrinsic limitation of the junction. No one has measured, no one has performed an experiment which conclusively proved that the junction had the problems that could not be cured by trivial methods. So, there's a huge reserve. If you use the junction, which, junctions now have intrinsic quality factors of 20 million or so. It's basically you have to think of the Josephson junction as a sort of hydrogen atom. The hydrogen atom, the intrinsic quality factor of the hydrogen atom is actually 20 million due to spontaneous emission. And the Josephson junctions are now at this level. That's enough. If you use the Josephson junction only as an ancilla, if it doesn't carry the weight of the memory, if it's just there as a nonlinear element for operation on a cavity, that 20 million is way sufficient for. It will carry us for a few years.
Thank you.
There was another question.
Would it be possible to use multiple modes of the cavity to store different qubits?
Yes, so we have not, this is something we have not played yet, but it's a good remark. So the cavities here have several modes, so they have different degrees of freedom, and this liberty can be used in this encoding. But here we have preferred, we are playing it safe. When we need 2 modes, we build 2 cavities. But you're absolutely right. We can use several modes of the same cavity.
This is an elementary question. So what exactly is the role of the Josephson junction? In the usual sort of like a transnormal qubit, the Josephson junction provides nonlinearity that's needed to truncate the system to 2 levels.
Yes.
Whereas here, you're using the coherent states of the cavity.
Yeah, so I can go in a little bit more detail. Yes, so the support of quantum information is actually this storage resonator. So it's basically an harmonic oscillator that is coupled to another harmonic oscillator, this radiative dome. by a transmon, but the transmon doesn't hold the quantum information. The role of the transmon here is just to provide this non-trivial coupling where two photons at a time are transferred from the storage to the radiative dump. And that's enough nonlinearity. This is actually a sufficiently general and universal nonlinearity that it can be manipulated to service the error correction mechanism of the storage. So if you want, if we go to, actually this error correction business started in the 17th century, where people started to invent escapement mechanism for pendulum, for clocks. How would you resupply energy in a clock, not touching the phase of the clock? So instead, I have quantum error correction is actually stabilizing a point on a 2D manifold, but classical clocks is actually stabilizing one point on a circle. And so in the escapement mechanism, you have very subtle cogs that are used to resupply energy. But the location of the time, the time is encoded in the oscillation of a linear pendulum, and the cogs are just there to resupply energy. Well, that's basically the role of the Josephson junction. It's a cog in a kind of general escapement mechanism.
More questions? Okay, let's thank our speaker again.
Thank you.
Are there announcements? No? Here she comes. Everybody hold your seat.